Hello test subject. Assignment 1 is now out. Hate and grief counseling will be available on submission. Aperture Science recommends strictly following all posted directions. Your grade will be determined by an algorithm. We wish you a pleasant stay.
Welcome back to Foundations of Algorithms, Test Subjects. For today, I want to point out our historical figure of the week, and this is Douglas Englebart, who is the founder of HCI and really kind of user experience design as well. He is famous for the mother of all demos, where he previewed a whole bunch of technologies that had never been seen, never been invented before. These included the computer mouse, the windowed operating environment, a word processor with the ability to go back and edit text that you've already written in. And now all of these things seem like, well, isn't that like part of the everyday computer experience? But up until some of Douglas Englebart's inventions, a lot of computing was done strictly based on a terminal interface. So you would type your text into the command line, you would get something back, and that was it. No other way to interface with the machine. So one of the key ideas that Douglas Engelbart was responsible for was this notion that we have to understand not only how computers work, but we have to understand how people work when they're using computers. And this spawned a whole lot of different disciplines. So if you find that you are perhaps more the design sort or the creative sort, or you're interested in people, the field of human-computer interaction might be something that is of interest to you. So everything from what is the right way to design a web page such that it makes it easy for users, or what should the how many options in my menu should I have on my iPhone so that users get to do what they want in the fewest steps possible? Or what is the right design for a new piece of hardware that people will use to interact with a computer? So think maybe VR or little wheels that you can turn if you're doing something like color grading on the computer. All of these different things are part of human-computer interaction, which is a field that the University of Melbourne is actually very strong in, both in research and in some of our teaching. So I'd encourage you to check out some of our offerings. I will put them online for you a bit later so you can see all the exciting work being done in HCI and HRI, human-robot interaction, here at the University of Melbourne. Now, one kind of fun story is one of my first ever primary school girlfriends was Doug Englebart's granddaughter. When my dad was a lot younger, we moved the family for a year to America, and I went to public school, and the love of my life at age 6 years old was Doug Englebart's granddaughter. We've had a guest from Aperture Laboratories telling us about the assignment. We've had a guest from Silicon Valley. But now here's a guest who's much closer to my heart, and I think many of yours. Some of you may remember a certain tour that happened last year, probably the largest tour in history. That is right. Today is all about Taylor Swift. And how many of you went to the Eras Tour? Anyone here? Only one? Do you have a friendship bracelet to swap? Hopeless. Okay, we'll get to that later. But our problem for today and for the next lecture is going to be looking at ticket distribution. So as many of you know, these tickets were in very hot demand. What about Billie Eilish? Anyone go to Billie? No? Okay, what concerts have you been to recently? Anything? Or shows? Comedy? Okay, Darcy, what have you been to? Jesus Christ Superstar, okay. Max?
I didn't go, but I was working at a Luke Combs concert.
Luke Combs, okay.
Minecraft, the movie.
Mal went to Minecraft. Were tickets for that really so sold out? I hear it's very high energy, very, very Jack Black. Okay, so this is our problem. We have a limited number of tickets, and we want to distribute them fairly. So let's say you're worried about Taylor Swift concert tickets selling out. What is the fairest way to distribute tickets? If you're the distributor of the tickets, what's the fairest way to do it? And it was Catherine, right?
Give it to whoever's first in line.
First in line, that sounds pretty good. So first come, first serve. So just paint me a picture of what happens. It's 5 a.m. on the morning, the tickets are meant to be released at the box office. What happens?
Whoever's first in line will get the tickets first, and
Well, how does the line start?
whoever shows up first.
Okay, so do you want to show up? Come to our box office over here. And who wants to be distributing the tickets? It was Ella, right? Okay, you're the Swiftie in the room, so you can come up and be our box office distributor. Okay, Catherine, but the box office isn't open yet, so what probably is happening between 5 a.m. and 10 a.m.?
People are fighting to be first.
Okay, well, let's assume we're in Melbourne and people are well behaved. Ella, you can come over here and be our distributor, but you're currently closed for business. Maybe come over here. You're off enjoying your morning tea. Okay, so other people are coming, right?
Yep.
So let's get a couple more people down from the audience. Mouse, yeah, you're lining up for Taylor Swift tickets now. Sia, do you want to come down and line up as well? Thank you. And now, looks to be about 11 a.m. Ella stretches. Give us a good stretch. Okay, and the box office is now open. So what happens? So go over and open the box office. You can go over to this side because we've got this big table in the way.
Welcome. Hello.
Okay, what happens?
I'd like a ticket, please.
Here you go.
Thank you.
Here you go.
Thank you.
I got to get them.
Wait, Catherine, do you go back to the back of the line? Once you've got one ticket,
okay.
you want a second ticket. Okay, so let's reset this again. Let's go back. And now let's start to think a bit more algorithmically. So Catherine, you've got the microphone for the minute. What data structure do you think should represent this queue? Okay, let's try and break it down a little more. We have lots of what waiting in line?
People.
Lots of people and lots of one type of object. When we want to store lots of one type of object, what do we use? An array. Okay, so we've got this big array and you're in position what in the array?
0.
You're in position 0 and Mal is in position
1.
1 and Sia 2. Okay, so we start distributing tickets from position
0.
0. Okay, so let's give this a go.
Thank you.
Okay, and now what's happening? Describe what's happening to the array.
Now the index is, you're adding 1 to the index.
Okay, so we could add 1 to the index, in which case you stay here, but Ella is going to move over 1. Let's give Ella a microphone so she can do a good job of distributing the tickets.
Thank you. Here you go.
Thank you.
Here you go.
Okay, so one option for us is to increase the index every time, but now you're stuck here.
Yeah.
Right? You're still here. So that's one solution. And now what happens, let's say we've made an array of size 3. And what happens if Aaron wants to come get a ticket as well? Aaron, do you want to come down to the front? Some exercise in the morning. Wait, where are you? There's only room for 3 here.
Yeah, you can't expand it, can you?
Okay, let's give it to Aaron.
Thanks.
It's on.
Yeah, all right. What's up?
So what's the problem?
Well, I can't join the array because it's an array of size 3. So it's defined with 3.
Okay, so give us some options. What could we do?
You could create a new array, make that size 4, but that sounds kind of inefficient.
Okay, so let's just try that.
Okay.
Okay, so we've created an array of size 4, and now what do we have to do?
Just copy over all the memory,
Okay.
the first 3.
Okay. You can have your copy.
Sick.
And now you're ready to go in.
Sure.
Okay. So that's one option. Let's reset that back. That seemed like a lot of work. I had to go over to each individual person and copy them over. Okay, reset the line. Aaron, I need more ideas.
All right. Well, you could just like clear the 3 that's already been like processed and then
Let's say
add.
just Catherine's received her ticket so far.
Sure.
Okay, so Ella gives a ticket to Catherine. And now what do we do?
Remove her from the queue, increment them up by 1, and then add me to the end.
Okay, wait a second. So we remove Catherine. So go sit down in the front row for a minute. And now we've still got position 0 empty here. What are we going to do?
Move him to position 0.
Okay, I'm going to do a copy and another copy.
And now I can go
I mean,
last
technically,
position.
Scia's still here. There's a copy of him here, but you can overwrite
Sure.
that one. We
He's
only
good.
need one Scia. I think one's more than enough.
Fair.
Okay, so we had to do 2 copies there, and we had to do 3 copies in this one. Still doing a lot of copies. Okay, let's reset once more.
All right.
Maybe we can combine these 2 ideas, that Catherine's original idea and your idea a little bit.
What was your original idea again, Catherine?
Her idea was just, well, we move Ella along. We increment Ella's pointer instead to point to different places in the array. Okay, so let's maybe do something clever. So let's move Ella along 1. She's given Catherine the ticket already,
Yeah.
Thank you.
and now is standing next to Mal. What do we know about this position over here?
Well, we know it's already been visited, so it already has a ticket.
Yeah.
So we
what
can-
could we potentially do with you?
Well, you could move me to the first.
Okay, come
Position.
here, and I'm sorry, Catherine, you're going to be overwritten.
Yep.
Okay, back to the front row, Catherine, and Aaron is now in this position.
Sick.
What's going to happen now if we're distributing our tickets?
Well, she can just finish off with these 2.
Yeah, and then what happens?
Then come back to me.
Okay, so we have to know where the end of the array is.
Yeah, which is defined.
Pointer to where the person that was where the people are that have received tickets.
Yep.
So then we can keep track of where we're allowed to overwrite and not overwrite. So this was our option 1, an array. But what are some of the frustrations that we were having just now with using this model?
It's a defined n, which was the original problem, right? So you can't actually expand it.
Yeah, so we could have expanded if we'd used malloc and realloc, but that was the same thing we were doing here, which involves copying. And so it's not very easy as people come and go to deal with these incomings and outgoings. We need to do a lot of operations,
Right.
which in big O terms, so if I am creating a new array and then copying all the items in the prior one over, that is big O of
N, right?
big O of n. And if I am, and the other issue we were having, well, if we had a fixed size array, then we were using big O of n memory when we didn't actually need to store all the people. We just needed to store the number of people that are in the queue at the current time.
Right.
So either way, we're doing some wastage here. So let's all go back to the front row for the minute. And we're going to come up with something new. Don't worry, I'll have you back down here in a few seconds.
That's great.
Unless you want to go back and we can pick a new crew.
That's
We're okay. So for arrays, how long did it take in big O to insert something at the very end of it, if there was room in the array?
Well, if you're just inserting at the end,
Yep.
correct, it's just adding 1, correct?
Which is O of,
O of 1?
yep, O of 1. Okay, now I'm going to introduce some new terminology for us, which is push and pop. Push means to put something at the front, and pop means to put something take it away from the front and put the start at the new place. So if we want to put something new at the front, if we say like, we've got a VIP who's come along,
Right.
how long is it going to take us to put that VIP in at the front of the line?
Must just be O of 1, right? You just have to read the first index and override it.
That's if we're allowing overriding, but Catherine's going to get very angry if she's now not second. Right? And Mal is going to be angry if he's not now third. Maybe they can deal with having a VIP take the very first spot. But so how many operations do we have to do to make that happen?
Well, I know pop's taking it from the back.
We're going to take from the front.
Yeah. So you said push is putting into the front, correct?
Yeah.
So, I mean, you could just push me into the front, right? And then just continue indexing over the remaining
But
positions.
how long does it take to put you in the front there?
I'm thinking it'll take only O of 1, right?
But Catherine's there right now. So what do we have to do before we put you in that position?
We have to remove her?
Well, we just said we don't want to remove Catherine. You're a horrible human being. So we want her to be right after you still, right? So then would put her in the next position. But
Yep.
what's the problem with the next position?
You have to overwrite the next position and the next position and the next position. So it's O of n, right?
Yeah, so it ends up being O of n, which is pretty expensive. So we need something new. And these are my two friends who helped make our next prop. So if we can have our Swifties back to the front of the line. And we are going to introduce a new data structure that will be useful for handling these sorts of problems, where we have data coming in and going out. Specifically with this idea of a queue, it's going to prove very, very effective. So let's spread ourselves out along here to make it a little easier for everyone in our audience to see. So maybe let's go in a bit of a line, just for the minute. Mal, you can come out the front. You're big brain for today.
Oh.
Okay, so someone new comes along. And what we're going to do, like we do in C, we're probably going to have a struct or something like that that will contain the information about them. So the name, how much money they have, their favorite Taylor Swift song.
Right where you left me.
Right where you left me. Okay. So I think we've created the first node in our data structure. So do you want to come over here? And you are Ella, right where you left me. Let's say you have now negative $300 because you bought a B reserve ticket. Should we upgrade you to a floor ticket?
No, that was what I had.
Okay. B reserve ticket?
Yeah.
Okay. So we're going to call Ella the head of our new data structure because she's the front of the line. And once she gets her ticket, then whoever is at the front of the line, the new front of the line, will then become our new head. So someone else comes along. So Mal, who do you want to let be second in line? Okay, Catherine comes along. But instead of putting her in an array, what we're going to do is we're going to create a link between the two of them. So figure out how to link yourselves. There we go. And now the great thing here is you don't actually have to be next to each other in memory. So while she's waiting, Catherine can go and grab a coffee somewhere over a little further back. Okay, Mal, what happens now?
If we added her into the new header, then give her ticket and maybe next person is being added too for the next time.
So let's add someone else to the line. The box office is still closed. Okay, so who are we going to add? You can pick out of the two. Aaron. Okay, Aaron joins the line. And Sia's been a bit lazy this morning, so he's still not on the line yet. He's just hanging out there. Okay, now let's say our box office opens. You can be the box office now. And you're going to sell a ticket to Ella.
Hello, here's your ticket.
Thank you very much.
And now what should happen?
Well, since she's getting her ticket, so she could be kind of like removed from.
Yeah, she doesn't want to be in the line anymore. She wants to actually go see the show. So, and you can go sit down for a second or out of the way. And now Catherine is at the head of the line, but she doesn't actually need to move anywhere specifically. We're just keeping track of the fact that now she is at the very front. And now Sia wants to join. He's finally woken up. What happens?
I'll give her ticket.
Well, Sia's woken up. He's ready to join the line before we give another ticket.
Oh, you connect with him.
So what tool in C do you think we could use to do this sort of thing?
Structure.
Okay, well, the structure just represents the individual person, but what about the links?
The pointer.
Pointers, exactly. We're all in different places in memory. We had Ella over here and Catherine over there. And the key thing we needed in our structure to be able to make this sort of diagram work was a pointer. So in this case, everyone has a pointer to the person behind them in the line. Okay, so let's bring Ella back for a second. And let's start thinking about the big O of all our operations. So let's say we want to add Ella to the front of the line. How many operations do we have to do?
Just once.
Just one? Okay, let's do the operation. Okay, what about if we want to remove her from the front of the line?
Also just one.
Also just one. Okay, what about removing someone from the back of the line?
We need to firstly find who's the first position and then get back till the last.
Very clever. So there are two ways of potentially addressing this. One, we could keep two variables in our computer's memory. one variable that tells us where the front is and where the end is. But if every structure only has knowledge of who's behind them, but not who's in front of them, then we run into some trouble. So let's go start at the front. So if we want to remove someone from the end, what do we do?
Firstly, we found that who's at the first, and then you're the second.
Mal, you're going to need to hold the microphone up further.
Uh,
So Catherine, come over here a little so we can follow this out. So Mal, you've got Catherine, who's the current head of the line.
I know Catherine she's the first, and then I find.
So we follow the link.
Oh,
Whoop. And we find Aaron here.
and we kept going. Ooh. You're the last.
And how do we know that he's the person at the end of the line?
I'll keep. Huh? What's another person?
Exactly. So we have a pointer that goes to nowhere. What kind of pointer goes to nowhere? A null pointer. So if we get to the end of our, what we're going to call a linked list, and we find no pointer from an item that we're currently looking at, we know that we've reached the end and therefore that we're at the last item. So how do we remove the last item?
You disconnect. with
Wait,
him.
but he doesn't know about the person before him. He only knows about the person after him.
So you have to disconnect with him.
Yeah, so what we have to do is we have to find our second last node, and then our second last node is going to destroy his pointer to the last node. There we go. And now we've only got 2 people left in our Taylor Swift line. So Xia, you can rejoin for a minute. And now let's say Ella's been a bit devious. She didn't want to wake up at 5 a.m. for the box office, but she's good friends with Aaron, and Aaron's going to let her cut in line. So how long does, wait before you do it, how long is this operation going to take? How do we do it?
Firstly, just to grab that since cutting the line, and then we grab him.
So we start at the start of the line.
Yeah.
Yeah.
And we search since cutting line for this position.
How do we know it's that position? We know she needs to be next to Aaron. That's Aaron over there.
Oh, you're here. And then we could disconnect. You disconnect with him.
So we have to go then back 1
Yeah.
and insert her at that position. So Catherine, we have to keep track of where Aaron is because otherwise we lose that part of the line, so we're going to have to keep an extra variable to keep track of where Aaron is. Now Catherine can plug into Ella. Our head plugs into the node we want to insert. And now Ella, we've kept Aaron as a variable where his location is. And so now we can plug him in. So let's say we don't know where Aaron is in the whole linked list. What is the big O time to find him?
Well, firstly, you have to find the position, so that might be n times.
Yeah, it could be, in worst case, n steps, because there are n items, and to go through it, we've got to go through, in the worst case, we're going to have to go through everyone in the line following every link in order to find the one that we want. Which means that if we want to insert at an arbitrary position, what's the big O time of that going to be?
That would be ON.
ON as well. Like say you don't know what the user is going to input. They might input the 7th position or the 9th position. In the worst case, you're going to have to insert them all the way at the end. And to get to the end, we have to follow each of the links along. It's not like in our array, which was O of what to put something at the end. Our array was, Mal, do you remember? How long does it take to put something at the nth position in an array? Of 1. Like if you want to put something in position 7, you just write A7 equals item, and then you put it in. So this is a big difference with our linked list. We've lost the ability to put something quickly at an arbitrary position, but what have we gained? What was much easier here?
Well, we are pretty easy to just insert and remove.
Well, it wasn't easier to insert anywhere. If we wanted to insert it at an arbitrary position, it was O of n. Which operations were really fast?
Insert or remove in the first position.
Yeah, inserting or removing the first position. And now we can do something clever. Now let's say that everyone is keeping track both of the person in front of them and the person behind them. Now what can we do?
Well, if we want to kind of like, for example, remove some person, we could just start from the first and we search and if we just like this, find the person and we could just disconnect and have something reconnect with them.
Yeah, so we're still going to need it,
Simultaneously.
even in that model, we're still going to need to keep track of a bunch of variables because we need to keep track of who the person that previously was before them and who the person was previously after them so that we can reconnect those. But let's say that everyone's got a pointer both forwards and backwards and we know where the last item is. What extra operation can we do cheaply?
We could insert or remove in the end quickly.
Yeah, because if you have a pointer if everyone has pointers all the way forwards and pointers all the way backwards, and you've got pointers to the start and the end, or what we call the head and the tail, then the head and the tail are really no different from each other. You've got a symmetric data structure, and so operations that are O of 1 to affect the head should be O of 1 to affect the tail as well. Okay, big round of applause for our Swifties. Maybe there'll be friendship bracelets to follow. Okay, so this is a bit of an easy one now, just to refresh our memory about what happened. What is the benefit of using a linked list? Where might this be something that we'd want to use, and where would you use it? Give me a couple of examples.
I think you can use it for a stack because I remember in the stack where you have a whole bunch of functions coming in, you usually pop and push at the first position.
Yeah, so we can implement a stack very efficiently with a linked list, but that's kind of abstract. That's not like a real life scenario. Can you think of a place where you might use a stack?
Maybe putting my clothes in the dishwasher. In the washing machine.
Yeah, so that's a little too real life. We want like a task that you do using a computer, but that's not just about the computer.
Can't think of anything.
Okay, maybe we'll give it to Tim. Microphone to Tim over there.
Maybe if you have some kind of service where you're taking in requests, right? Like, I don't know, you have like a Magic 8 Ball website and you've got people querying your Magic 8 Ball, and you need to give each one an answer. It's very similar to the movie cube, just a digital analog. So any time where you basically have a digital queue, this could be useful because every time you pop one in or take one out, it's only the O of 1 rather than O of n for an array.
And digital queues show up all kinds of places. Imagine you're making requests to any kind of web service. You normally want those requests to be handled in the order that they arrived. You don't want the person who just sent a request to visit google.com to be prioritized above the people who sent a request 30 milliseconds ago. And so there are many, many instances in real life programming, but also in the real world as well, where this kind of data structure would be more efficient. Tim, you can keep holding onto the microphone for a second. I got another 3 backups over here, and who knows if you'll need it again soon. Okay, so the key thing that we actually need in order to be able to implement these in C or in most programming languages is some way of referring to different objects located in different places in memory. And the way we do this in C is with, say one more time, pointers. Okay, so now once the computer starts up again, we are ready to try writing the structure that we'd need to contain this kind of information and to build our linked list. Okay, so what are the ingredients that I need in my object for a linked list?
Well, you'll need somewhere to specify where the linked list starts in memory.
Okay, so I'm going to need
So the first element, a pointer to the first element.
Okay, pointer to the first element. And the first element we called head, right?
Yeah.
Okay, but that's just a pointer to a blank chunk of memory.
I think every single element in the list needs to have 2 parts, right? Sorry, the linked list, yeah. It needs to have the actual content, so the query in the queue or whatever it is, and then also the pointer to the next element. So it's kind of like your pointer is pointing to an element, but also it needs to point to another pointer.
So maybe let's go back to our Taylor Swift example and use people's names as
Sure.
the data. So what can I use in C if I've already asked this question, but what can I use in C? Tim, let everyone else answer this. What can I use in C if I want to combine lots of different pieces of data in one entity, in one object? Yeah, use a struct. Okay, so let's create a struct, and what should we call this? Tim?
Name and pointer element.
Well, what I want to do here is I want to have like an element of my
Linked list element.
linked list element. So I could call it linked list element T, but that's getting kind of long. And so what I'm going to do is I'm just going to make a type def for a node. And now I can define my node like that, just normal struct syntax. And so what things do I want in my node?
So we'll want a character array for our name string.
So we're going to be cool and use dynamic allocation for our names right now. So right now there's no additional memory other than the pointer to the set of characters that we have here. So this is keeping our structure nice and small. And what else do we need for this to actually be a node?
We need a pointer to the next node.
So what is the type of a node?
The type of a node is a pointer. Oh, sorry. A node. Type of a node is a node.
Except in this case, we've got a node T,
Yeah.
because that's what I've defined up here. Now, the problem that we'd run into otherwise is in our definition of node, would be referring to node. And so that's why we have that type def out the front to let the compiler know that the definition of a node is going to come subsequently. And then by using a node T here, we're going to allow ourselves to refer to our incomplete definition earlier up the top, which will then be filled out by the compiler once it reads it.
Can I just ask one question there? Why are we having the node itself as a attribute of a node? Why wouldn't it be the pointer to the next node as the attribute?
Yeah, that is correct. I just hadn't written the star in yet.
Oh, sorry. Yeah.
Yeah, so we need a pointer to who is next. And in our fancy symmetrical version, what did we also have?
An end?
Well, we had an end. But should these be void stars?
Yes.
Well, I mean, they could be because a void star always works to point.
Oh, sorry. And there should be nodes, right?
Sorry, say that again. I missed it.
Should they not be nodes too?
Yeah, these are nodes as well. They should be pointers to nodes.
And I guess we'd also want, a node for the previous if we want to make it symmetrical.
And that is all you really need to start to define what a linked list is. And now all we need to do is to actually start building these connections between different things. Now, one thing I will note is what I've created right here is going to be a doubly linked list, which means it has pointers both forwards and backwards. But a lot of linked lists, and particularly discussion of linked lists that you'll see, is about singly linked lists. And we've talked about already some of the advantages of doing it doubly. But for now, I'm going to make our lives simpler and just take that away. So let's...
Could you have like I was probably getting a little bit too crazy, but could you have a 2D linked list like for like I don't know, like the map that we have in the assignment? Could you have, a 2D linked list which you can do crazy stuff like snipping the bottom and attaching into the top? And
that is no longer a list then. That's a different data structure with different properties, but we will talk about them. We'll talk about them maybe later in today's class, and if not, we will talk about them over the next couple of weeks. So let's define print list, and print list is going to take in node T head, and now let's actually write this function, and I'm going to give the microphone to someone else, and these should all be pointers. We're going to fill this out. Okay, you can turn that on mute for the minute. Okay, Karen, you're going to help me write my print list function.
Okay.
Okay, so our goal here is to print everything that is, all the different names that are included in our linked list, starting from the head and going all the way to the tail. Do you think you can help me out with the first line?
No.
Okay, so let's say we're looking at a node right now. We're looking at the head.
Okay.
And every head has a name. How do we print the name?
So
What
it's
function do we use in C to print?
print F.
Printf. Okay, so let's include standard io.h because we remember if we forget that, there's no printf. And now what do I type? If I want to print the name.
Print.
Yeah, you're right.
Head. Like the pointer.
Say a bit louder.
Print F and then is it a character?
Yeah, then I use the quotation marks. What do I put in the quotation marks? What do I use to print a string in printf? Do you remember?
The percentage sign.
Percentage sign.
Char.
There's a char. It's for a string. We don't want to just print one character.
String.
Yep, which is what letter?
S.
S, there we go. And then I just add my argument in there. So I printed one node, but now I want to print the next node. And well, we could use the same sort of syntax to get the next node. So let's create another node T next. And this could be head, what would I write there? So our node has name and it has a next. So which of these am I going to pick?
Next.
Next. And then I could copy this line over here. And what would I change it to?
Next.
What would I change here?
Next.
Yeah, I'd write next. Okay. Now I want to print the next one as well. So I guess that's the next one. So I could write node T next. And then what would this be?
Head next.
Well, head next is just the second one, and I want to get to the third one. So this is next, right?
Yeah.
So I could do next. And then I do my printf. And which one am I going to print now?
Next.
Next. Okay, so I've done 3 of them. What am I going to do now if I want to get the 4th one?
Same thing, but that's kind of like inefficient.
Okay, so what do we do when we're repeating the same thing over and over in C?
Loop.
We'll use a loop. Okay, see, you're getting the hang of it. Okay, so let's set up our loop. And what did we say about when we know that we're at the last element? How do we know that we're at the very end of the list? Now you'll remember, I think it was Xia was standing at the end here and he moved his hand into the blank. What did we say was there? Null, yeah. So we know that when the current item that we're looking at, when its pointer points to null, then we're done. So while current.next does not equal null, do stuff. But now I've used a current variable, so I should probably keep track of that. Oh, these should be, I messed up here. These should be pointers. There we go. So we should create node current. And what is the very first item that we're going to start looking at? Ella, was it? Not Ella. What was your name again?
Karen.
Karen, sorry. What was the very first item to start this whole process with?
Head name.
It was the head. So let's start off with the head. And then what was the thing we want to do with the element?
Print.
Yeah, we want to print. So tell me what to write.
Print F. quotation mark,
Oop.
S, head.
And then,
The head, and then,
well, now we're not working with the head now. Now we're working
Oh.
with car, right?
yeah,
So what do?
car.
So we would do car. Do we want to print all of car? Or what are we trying to print? What do we do down here? What were we printing? We weren't printing car. We were printing car heads, printing the name, right?
Yeah.
Because we can't print the whole node. That doesn't make much sense. We want to print the specific piece of data that it's carrying. So we can print car.name. And now we probably also want to add new lines or something just to clean up our output. And that is actually pretty simple. Now we don't need any of that stuff. And we're done. See, fairly short function, but the logic of it takes a little bit to work through. And if you remember the demo that we had and the steps that we went through, it might be helpful. Except, what are we missing? The loop runs, and what happens when the loop runs a second time? It's going to print the same thing, right? Okay, how do we increment, Chi?
We're trying to increment the nodes.
Well, we can't increment the node, but we're trying to get to the next node. Right? So how do we get to the next node?
Can we use index?
Well, we can't use indexes. There's no array. These are scattered all in different places in memory. But we know how to get to the next node, don't we? Chi, what does our node have that tells us how to get to the next one?
Pointers?
We have a pointer to the next node. So in here, what should I do? What should I do with the pointer? Should I look at it?
Yeah.
And then do what? I can stare at pointers all day, but I'm sure you would all get very bored.
I'm not sure.
We're going to follow the pointer, right? We have to follow the pointer, and then we want to increment the thing that we're looking at so that our new current item is the next one along. So if we're currently here and we see a pointer that's over there, let's, instead of this being our current node, let's step over to the next person, and this should be our new current node. So writing that in code, that'll just be current equals current.next. So this says follow the pointer, and once you've followed the pointer, you can forget that first node. Your new node that you're looking at is this one. So now we're actually done. Okay, questions about print lists so far? Ethan?
Just wanted to check if that will print the last node.
This will not currently print the last node. So if we want to print the last node, then we'll have to do that. There is another, depending on exactly how you structure it, you can also make it so that the last node with a null pointer doesn't have any data attached to it. It's just a marker node for the end. So there are a bunch of different tricks you can use to make your code a little cleaner and neater, depending on exactly what you're optimizing for. But very good point. Okay. So now let's look at some pre-prepared code. Okay. So what I have here is a hash define for an insert at end function. And insert at end is really the same as insert at index n or index y, where y is the last index of the array, at least for a singly linked list. If I tell you insert it at the end and I tell you that the end is at position number 6, they're equivalent, right? So that's all I'm doing in my hash define here. In this instance, I've actually, instead of doing dynamic allocation for the names, I've set it to a fixed size just to make our code a little bit simpler for us to run this. And then I have the same thing as I had before, except now I have swapped out my name there for a data T. And the reason I might want to do that is so that my linked list code that talks about how to deal with a linked list is flexible. So I can change data t to an integer, I can change it to a name, I can change it to whatever I like and just swap it out. The core element here is not that it is a person with a link, it's that it's a node with a link, and then nodes can contain whatever kind of data that we want them to. And then I have my push function, I have a list length function, and I have my inserted index function and a pop function. And then we'll see our example in a minute. So let's write a version of the list length function really, really quickly. And maybe who wants to have a go at writing this, who thinks they've got a good idea of how it might be done? Max? Okay, well, Max, you pointed, so you get the microphone. Tim, you've got it? You can pass it down. I'll give you a hint. It is very, very similar to the print function we just did. Okay, so let's do int list length, node t head. Okay, so we want to keep track of how many items in the list, right?
Yep.
What do we need to do that? To store how many items in the list?
Sure.
Or the length of it? Okay, maybe let's start with the return statement.
Yeah.
What are we returning from this?
The length of the list.
Okay, return length. Now we've used a variable, but we haven't declared it, so
Yeah. So we need to make a variable length into.
That should be int length.
Yep.
Okay, and now let's say, and now how do we figure out how many items are in the list?
Well, we could do the same thing as we did before, where we iterate through every value in the linked list.
Okay.
And then I would just like, once we do one iteration, just add one to the length.
So length plus plus, and then car equals car next.
And then you would need to set length to equal 0 as well first.
So I need to set length equal to 0 here. And what am I missing?
The check. Anyway.
What is car?
What's current?
What is car? The variables DUR.
The current.
But what am I missing? What does car look like to you? Okay, we have a line that should go right here.
Yep.
Right? Every variable needs a
Definition.
Yep. And have I got one for car?
No, you do not.
Okay, so what should car be?
Cur equals head.
Okay. And what do I need when I first declare a variable?
You need to say what type it is.
And what type is car?
It's a node T.
Node T something. Still missing one character. What is the type of the head?
A pointer.
Yep, that's it. Just needs a pointer. So the steps are, when you're working with a linked list, you typically need to be keeping track of at least the element that you're currently looking at. And then as you go through the linked list, you're going to update that to follow the link over to the next element that you're looking at, and all the way until, when do we stop? When do we stop, everyone?
Null pointer.
Yeah, when we get to the null pointer over there at the end. And that's what we're doing here. As long as the next thing is not the null pointer, we know we're still inside the list. Now, Ethan's point still stands here, which is that depending on exactly how you've set up your linked list, if your tail node has data in it, then you might have undercounted by 1 if we're counting length from 0. So you need to pay attention to these off by 1 errors just to make sure that if your head and your tail have data in them, that you're accounting for the fact that they're part of the linked list as well. And if they don't, depending on what exactly you want to get out of your length function, that you've calculated that correctly. So let's take a look at the list length function that was written earlier. List length. And we see almost the same thing, just with slightly shorter variable names. So I have my counter, which I've called I here. Instead of calling it car, I've called it P. P equals head. And then do the same thing over and over and over until... Now this is another interesting way of doing it. What we're doing here is instead of having the check for what the next element is, instead of doing that, what we're doing is we're letting P be the pointer, we're following it along, but if we've gotten to it and it's a 0 value, then that while loop is going to evaluate to false and it's going to terminate. So that's the other way of doing it, is by advancing the pointer, instead of checking what's next, just get that value, and before you actually dereference it, because what happens if we dereference a null pointer? Segfault, yeah. So we don't want to get a segfault. So before we dereference it, we make sure that it is indeed a non-zero value. If it's a negative value, something's gone seriously wrong, and we'll handle that elsewhere in our code when we're setting up the linked list in the first place. Okay, so we've got our print function, which was as discussed before, as Karen constructed for us. We have our list length function that Max built for us. And now let's actually get to building the list itself. So the very first thing we need, given that we're dealing with pointers, is we need to actually get the computer to set aside some memory for our linked list. And so we're doing that with malloc, and you'll see now we're using the size of operator, but instead of using it on one of the basic C types, like size of a pointer or size of an integer, the compiler is actually able to get for us the size of our structure. So it's able to tell us the size of memory that we need to fill out a complete node T. So let's allocate enough space to contain an entire node. Then we're going to use our technique of having assertions. And then the very first thing we want to do is, now that we've allocated that memory, we need to fill out the 2 different components of our node. Because our node right now, it has a location in memory, so if we got its address, that'd be a valid address for us to use, but there's nothing there yet. So what we need to do is we need to put something in the next pointer, and we also need to put something in the name. The 2 different components of our struct that were created over here. Or in the data, sorry, because we called it data instead of name in this instance. So head will be null because we don't currently have a second item. There's no one else waiting in the line to connect up to. It's just the head alone there. So let's create the space for it, have the pointer set to null because it is the one and only element of the list. And then the next thing we're going to do is copy some data into that space that we reserved for the name. Now notice that we can do this because in this instance we declared our name T as having pre-allocated an array of 20 characters in size. So if a data T is a name T and a name T is an array of 20 characters and our node has a data T which is a name T which is an array of 20 characters, when we use size of to figure out how large that structure is, it's going to have room already reserved for a set of 20 characters. Also for that next pointer, it might also have some additional data just to allow it to be very efficient, because sometimes when you space things in memory, the computer is going to want to add spaces so that everything aligns nicely inside. And then we're able to copy our data in. Now, who's got the microphones right now? I think one is with Max. Max, it was Ben or Sam? I've forgotten. Sam. Do you want to pass it to Sam? So can I copy in a name of 20 characters in length into the data, and why or why not?
How much space did we allocate again for the?
So let's scroll up.
No, no, you can't, because if it's 20 characters, but it's a string, it also needs like the terminating character at the end, so it'd have to be 21.
And terminating character for a string is
Is it a null byte?
a null byte, but with only one L instead of two L's. So it is, let me just put that in a comment. It is a null byte. Oh, whoops. It's a null byte, which we represent in C with that, with a /0. But string copy is going to handle that automatically for us, so we don't need to worry about it. And so at the end of this instruction, we are now going to have a correctly instantiated head. Okay, now let's do insert at end. And let's look at how we defined insert at end. So insert at end was, as we said before, this function insert at index, but where the index that we're inserting at is the list length. So I guess now we've already finished writing list length. Let's look at insert at index. And here is a fun VS Code tip. If you press F12 on your keyboard, it will zip you to wherever that function was defined. So that helps you move around faster, just a nice quality of life improvement. So insert an index. This was the same thing that we had before, where Ella came along and wanted to stand next to Aaron, who was somewhere at some position in the list. With the exception that instead of looking for Aaron by name, we're just going to go to a certain index. So let's say we know Aaron's at index 3 and we want to insert Ella at index 3. That's what this function is designed to do. So the first parameter here is going to be the data that we eventually want to be in that node once we've created it at that new position. We are going to need the head, the location at which we're going to start looking through the list. And we also need the index, which is just the location at which we're going to do the insert. Now, note here that instead of calling this head, I've called this P. It would be very similar if I did it this way. So let's say I call it head, just for clarity. And now I do node T P equals head, which was the way we were writing it before, just to get used to it. We can call that P, or where I called it current in one of the demos before. This is having it defined ahead of time is okay to have that in the set of parameters. Why? Well, once we've moved on from the head, in this function, we're not going to be going back to it, so it's okay if we overwrite that pointer, that temporary variable inside this function, to be pointing to the next thing. Because once we've moved past the head, we're never going back to it. So that's why I can reuse that variable name. So first step is probably to create a pointer to the new node that I'm going to insert. So let's say we're inserting Ella. Let's create a node that will contain her information. I also have a counter variable here. So let's malloc some space for our new node. Fill the new node with the data that was given to us as input in the function. And then let's start off just by setting its next pointer to null. This is just the same thing that we did before when creating the head from scratch. We're creating a new node here. Now comes the slightly tricky bit, which is figuring out, number one, how to iterate through our list, which we've already done twice already in our list length function and in our print length function. But now what we need to do is we need to go and iterate through it only up until we get to the ith position, or the indexeth position, I should say. So that's what we're going to do here. And once we get to, this is if index is 0, sorry. The first case is if they've asked to insert it at the very start of the list. If they have asked to insert it at the very start of the list, so if index equals 0, then actually this will be useful with two people. So Mal and Sia, do you want to get back up for a second? So you are the existing head, Sia's the existing head, and Mal is our new node that we've just created. So Sia, do you want to come over here just so we can all see it a bit better? So that is our head, and this is our new node. Our head, Sia, currently, what are you pointing to? What does your next pointer point to?
Null.
Null. I'm losing microphones at an alarming rate here. Red, 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 green. Okay. Sia, you're pointing to?
Null.
Okay, so Sia next is null. And now, Mel, what do we need to do to make you the head of the list?
Well, we need to define head as
Yeah, so we've created you, we've created your node, we've filled in your name, and now what do we do with your next pointer?
well, my next pointer should be pointed to.
Yeah, because if you're going to be the new head, you're going to attach your next pointer to Xia. And that's exactly what we're doing here. We say new dash next equals P. And then once we're done, we just return the address of the new head of the list. So you'll see our node T inserted index allows us to return a pointer to the head of the list. In most cases, we're not going to be changing the head. And so we'd return, if we were in the instance before and we were attaching Mal to the end, Mal, just attach yourself on the other side. So now your Xia's next. In this instance, we're just going to return Xia because he's still the head. We haven't changed it. But in the other example that we had right before, where we wanted to insert an index 0, we do have a new head. And so we're going to return Mal's address in that instance. Okay, you can both go back down for a second. Keep those for the minute, though, in case we need them again. So that's our case where index equals 0, which is our special case here. And you'll notice that at the end of that case, we return. So we don't run the rest of the function. In all the rest of the cases, the first thing we need to do is hop along all of the links up until we've gotten to the correct index. So this is not for index 0. This is, for example, index 1. We did kind of a very quick example of that right there. So if we want to insert it at index 1, we're going to hop along up until the node right before the place that we're going to put it. Because if we're putting it at index 1, there's currently nothing there, so we can't hop along to that first one because it's just Xia here on his own. He's pointing to null. So we actually have to stop when we get to the 0th node. So now we're at the 0th node. The place for node in position 1 is going to be to my left here, pointed to my next pointer, and that's when we would stop. Now let's say we want to put a node in position not 0, not 1, but in position 2. So you visit position 0, you visit position 1, and now you put it after position 1 over there. So you connect position 1's next pointer to the new node that we've just created over there. And that explains the loop bounds over here. So start at 0, go to index -1 because you can't go all the way to the index because you haven't actually created it yet. And each time you hop along, just follow the same logic that we were doing in our other steps. So change whatever the current node you're looking at to be the current node's next location. So current node, that's my next location, that's where my pointer's going. Okay, this is my new current node, okay? That's the next location. Okay, that's my new current node, which we're just calling P in this variable here. Now, once you're at the correct place to insert it, okay, so let's say that this is our list currently, and I've just asked for us to insert something at position 1. Inserting at position 1 means inserting it kind of in here, right in between Xia and Mal. So this is where Aaron's going to go, which is going to involve shifting some of these existing links because we can't like cut the link in two. So what we're going to do is we first stop right before, just like I said before, we're going to stop right before the place at which we want to put the link in, which was over here. So Xia is P currently. And now watch what we do. So new dash next, so Aaron is new in this instance. New, what he is pointing to as his next one is going to be what is currently P's next one. So P, Xia is currently P because we stopped at position 0, and his next pointer is Mal. So Aaron, what Aaron is going to point to when we're done, so Aaron, do you want to stand here for a second just temporarily? So Aaron's next pointer should be going to Mal. And that kind of makes sense. When we're finished with this, okay, so that'll plug in there. And now Aaron's next pointer is going to Mal. So that's step 1. And now P, which is Xia, where we stopped, his next pointer is now going to go to Aaron. So that means, yep, unplug that. You've got, cables have two ends, guys. Okay, now stretch out so everyone can see. And we've successfully inserted Aaron in the middle there. So those were our 3 steps. First step is get to the right location. Once you've gotten to the right location, set it up so that the one that you're just inserting now is pointing to its correct successor. And then go to the one that you were previously at and make sure that its successor is now connected to your new node. So maybe if you get confused while looking at the code, watch the visualization again and see if that helps you out. And then when we're done, we're returning P, and that finishes off our function. Okay, thank you very much, guys. Round of applause for our volunteers again. And now let's actually just test our code overall to see how it works, prove to you that I'm not just making things up. So I'm going to insert, I don't know why I've inserted min here 3 times, but we are going to insert a whole bunch of different nodes into our linked list. Let's, Ray, I don't remember how to spell your name. Remind me? That's right. Ray, that's Darcy, and who else? Darcy, who's to your right? Alex. Oh, that's one of the Alexes. Well, you know what? To be fair to our class, I think we need all the Alexes to be represented. Oh, which is the other Alex spelling? Like that? Okay, so Alex, you're spelled A-L-E-X? So do we have Alex 3 somewhere? No, he's not here today. Okay, so we'll just leave it at that. Okay. Oh, we want more? Anyone played Half-Life? By the time we're done, we'll have a class of just Alexes. Oh, okay, so let's compile. What did I call this? Insert n.c. Let's hope. Okay. It is giving me some warnings. Let me just check that. Yeah, I think these warnings are fine. I'll check what they were later on. Live coding sometimes results in minor errors. There we go. List length 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. We're correct. Okay, so Nick, Young, Nash, Flo, Rose, Ray, Darcy, Alex, and Alex. And then what I was doing next is I was just printing the current head of the linked list. So I was inserting all of these at the end, so the head should not have changed. Oh, sorry, that was print list. So that was printing the whole list, my bad. Then what I did is I was popping the first node off the linked list, so that should change the head of the linked list. So let's see if that correctly worked. Yes, Nick is no longer there. It now starts with Young. Print the linked list again, just so you could see that. Then let's pop another node off the top of the front of the linked list. Then print it once more, and now you can see that it starts with Nash. So I wasn't lying, linked lists actually do work.
So when you pop, you always have to do it as a new assignment to the head.
So there are a number of different ways of writing linked list code. One kind of fancy way, because I know you're into some of the more advanced stuff. One way of doing it is you have the head of the linked list as a pointer to a pointer, and then, yeah. And what that's essentially saying is this is going to be a variable that will change what address it's pointing to, like what the head is. So then what you can do is you can have linked list functions that modify what that pointer is eventually going to go to. So you go down one level of indirection, then you have a value that you can modify to adjust to the new head. So that's one way of writing linked list code. If you didn't follow that last 30 seconds, it doesn't matter. It's for those of you who are in our more comfortable stream. But otherwise, yes, the reason why you return the head from those functions is so that you can update it on the caller side. So the caller sets the head to be equal to the result of the function to allow you to update the new head. So there are a few ways of dealing with it. You might ask, well, what if I want to get the value of the thing that was just popped? That's an instance in which you might want to use one of the more sophisticated techniques to ensure that you both have the correct new head of the list and that you also have access to the thing that you just popped. Like a real life example of where we might do that is, let's say we had our line for the Taylor Swift tickets that we had at the start of the class with, I forget who was at the front of the line. Ella was the box office, but I forget who was at the front. In any case, the reason why you might want to do that is when someone reaches the front of the line and you're removing them from the front, you also at the same time are likely going to want to get some of the details about that specific node. And so that's why you might try some of these very slightly more advanced coding techniques for linked lists to allow you to do both of those things at once. Okay, now I have an example of, oh, it looks like it wasn't copied over properly. So I might have to write it myself, which is fine, of code with a bug in it. And the goal here, I'm going to leave everyone a couple of minutes to see if you can spot the bug with the linked list code. The way I'm going to encourage you to go about trying to solve this is to actually try and sketch it out on your, if you've got a tablet or a piece of paper, and if you don't, to try and step through the code briefly on your laptop to try and figure out what is going wrong in this code. So let's create a new file. And I'm going to copy some of just the key elements here so that I have my libraries, etc. And this is relevant to the discussion we just had. So you'll have to give me a minute to write this. But while I'm writing it, be watching for a bug. In fact, I'm going to throw in maybe a bonus bug. So we'll have 2 bugs. If there are 3 bugs, then that's on me, and you can call me out on that. So there may be extra bonus bugs. Am I? Okay, so there's my push function. I'm going to write my pop function. Okay, the bugs are already kind of introduced. So hopefully you can see we've got our list from our line. From our class, sorry. Okay. Give you one more minute to look over the code. It's going to be a little hard for me to display the entire thing, but the bug is in view right now. Bugs. I got all the bugs in sight.
One of the bugs that the first string copy is spelt wrong. Like
That was a bonus bug. That was a bonus bug. Okay, leave everyone with another minute. Ronald's got it, but we're gonna leave him a minute still, just to let everyone ponder it. I don't see many people drawing out the linked list, which is honestly the best way to kind of solve these sorts of problems and to debug it. You are going to end up using linked lists in assignment 2. And if you're not drawing them out or representing them in some way, you're going to have a hard time. First.
I think there's an error in line 19.
Sammy, another error? Yeah, that is one of the bugs.
That's the bug. And you should remove the dereference thing.
So in this case, it's not actually being used as a dereference. You're right, but it's not being used as a dereference operator here. It's being used as a type signature. So this says, what is the size of a pointer to a node T? And we don't actually want space for a pointer to a node. We want space for a whole node. So that was one of our bugs. Thank you, Chi. And now I think, Ronald, do you know where the other bug is? Nah. Okay, so you spotted that one as well. Okay, we'll leave everyone one more minute to spot the other bug.
I think that the way you've got it now, when you push Ray, you're making a new node with the data Ray and putting it in front, but you're not updating what your head is pointing to.
Exactly. Thank you. Can we have a small clap for Lotte? You got it. One of the things we just had this bit of a discussion about was about making sure that we had some way, whether that was using double pointers or the method that we did in detail right before, to make sure that you're updating what the head is. Because if you're putting something at position 0, at that very first position in the list, but your head is still pointing to the second thing, then you've kind of like lost that thing that you just put in the head altogether. You're always starting from later on in the list than the beginning. And so what we needed to do was have head equals push Ray, head equals push Ella, head equals push Karen. And now doing the same thing with pop. Now let's go to Tim's question about what we're doing here. Figured it out? Do you want to explain to everyone then maybe?
Basically,
microphone for Tim. I think Sam has one. So explain your question first again, and then explain the answer.
So my question was, why are we assigning old to P if we aren't then doing anything with that because we're freeing it? But the answer is that like old is not defined already. So like we're passing in for pop, we are basically passing in the head, right?
Yep.
And so then we are defining old as equaling the head. But then, like, we are then, but P, although we've passed it in as the head, does not have to remain the head.
Exactly.
So then P is now assigned to the second element after the current head. And once we have done that, then we can free the old head and we return the second element as the new head, which hopefully we will actually assign to head because we would have said head equals pop.
So what pop is doing is it's saying whatever is currently this first item over here, we eventually want to free that. Before we free it, let's make sure that we at least have a variable that's keeping track of what the new head will be. So let's see where that happens in our code. That's over here, P equals P.next. So let's stop looking at the current head and look at its successor, so that's P next, and this is going to be our new head that we'll return. So we're going to return P. But we also want to make sure that we're doing our respectable memory management. We're all excellent, safe, secure, and efficient coders here. And so we've got to keep track of our old head that we mallocked and make sure that we free it. So we've got to keep track of two things. We've got to keep track of the old head and the new head. The new head is P now that we're going to return, and the old head we're going to free. And that is how the pop function works. So let's take a look at better push pop, and here it is with the fixed version that I had prepared earlier in case I didn't spot my own bugs, or in case you didn't help me spot all of my own bugs. Okay, now let's look at another version. This one I'm not going to write from scratch. We will take a 10-minute break and give me time to copy over the next pre-prepared example over. While live coding is fun, I think we've had enough of that for one chunk, and then we'll do another bug finding exercise in 10 minutes at 11:46. Okay, we'll see you all in a few minutes. Welcome back, everyone, and I had a chance to get through almost the whole class of names. I think I was missing like 5 or 6 people there. If I missed you out, don't worry, we'll get a chance. I'll zip around the other way in our next break. Okay, so now we have a similar kind of exercise. We're going to do this one more time. In this example, I think there's only one bug, unless I've done a really bad job. But I will try and get us to the point where you can see what the bug is. Okay, so this time I'm going to show you something. I'm going to point out 1 or 2 features that will be relevant to spotting the bug, and we maybe won't spend as long. So I'm doing the same thing here. Can anyone just quickly see the difference? If you can, shout it out to what I was doing in the last example. What's different about my type definitions here? Darcy? So Darcy notes that in the last example, I was pre-allocating 20 characters for the string. In this example, now I'm allocating the string dynamically using malloc. Or I should be at least. And so you'll notice when I create a new node, and this is what I'm going to be doing in my functions, along with mallocing space for the node itself, I'm also going to malloc space for the string. So in this case, you can see I've created a string Albert that I have statically declared here. And what I'm going to do is I'm going to calculate the length of that string plus 1 space for the null byte, malloc enough space for that. So Albert is 6 characters. That gives us a malloc. We're mallocing room for seven characters because that's the 6 of Albert plus the null byte. And then head.data is just going to be a pointer to that now blank chunk of memory. Now that I have a blank chunk of memory that, well, it might not be blank, it could have junk in it. My bad. That chunk of memory that is allocated for our use, we now have to fill it up, and we're going to fill it up with Albert's name. So this is our new process for creating a node, is we create the node by mallocing space for the node. We set the next pointer to null until at such time as we're ready to join it up to the list. We malloc some space for the data, and then we fill the data up with whatever we want it to be. And so what I'm going to do here is I'm going to insert a bunch of nodes, just like before. If we look at my insert code, now I'm doing the malloc here for the data and doing a string copy to make sure that I actually copy that data over. So no major changes there just thus far, just adding in malloc into our playground. And now after this, I'm going to do correctly what I didn't do correctly before. When I pop an element from the list, I'm going to set the new head appropriately. So now for our bug hunters. I might have to reorder some of the code so that you can actually see the bug. And let's get this all scrolled. I'm going to remove some new lines, and then we'll have enough code on the screen for us at once to actually spot the bug. That should be zoomed in enough. Okay, spot the bug. You have 2 minutes. Okay, Lara, what was different about this block of code compared to the one that we just looked at before the break? What was the one big thing I changed?
It was something to do about strings.
Okay, so let's go back to the top for a second. Do you want me to put the other one right next to it?
Yes, please.
So let's look at the highlighted bit there. What's different?
We haven't set a specific size or amount for name T.
Yep. So that's the first step to spotting this bug, is to recognize that. And notice that here we've statically allocated the space for the name. So this means when we free a node, that we're going to free all the memory associated with it, because the node is this big thing that has room for those 20 characters and has room for the next pointer inside it. If we look at the node on this side, this node has 2 pointers in it. It's got a pointer to, we don't know what yet, but it will be the name, and a pointer to next. And so when we free the node, what we're doing is we're destroying those 2 pointers. Now, this is where kind of the tricky thing comes in. If we destroy a pointer, is that the same thing as destroying the thing the pointer points to?
No.
Okay, so let's look at what I'm doing when I'm destroying my list over here. So let's say I go into pop and I am intending to remove the head of the list and make the new head the second element. So let's go to our pop function. And this looks identical. This is the bad string again, and I'll open good string again. Here's the good one, and now let's look at their 2 pop functions. So there is pop. On this one is pop in the version where there's no bug, and this is pop in the version where there is a bug. But the insight is to put the ingredient that we just discussed like 30 seconds ago together with this pop function. So what is this pop function doing? What is it freeing?
The first.
So both of them are identical. So what are they freeing?
The head.
They're freeing the head. And in the case of this one, where we have the string itself, the memory for the string as part of the node, are we destroying that memory when we free the node? It's part of the node, it's part of the node itself, so are we freeing that memory?
Yes.
Yeah, we are. Now, what about in this one? When we free the node, are we also freeing the memory for the string?
I don't think so.
Exactly, that's the bug.
Yeah.
What we've done is in this bad string version, we have inside the node, we have a pointer to some other memory, and that memory has been allocated by a different call to malloc somewhere else in the program. But when we destroy the node, we're forgetting to clean up that memory as well. Because when we destroy the node, we're also going to lose our pointer to that memory. And when we've lost the pointer to the memory, it's kind of just been abandoned there. There's no pointer to it, but we never freed it. And so the big mistake in bad string here is if you have a struct or a more complicated object in C that has mallocs inside of it, that has pointers that you're later setting, you have to remember when you clean up your structure that you also have to clean up all the mallocs that were used to create it. So if you had one malloc that created the object, and as in this one, where that one malloc was sufficient to populate the entire object, then you don't need to worry about the other 3. In this one, where there were 2 calls to malloc, there was a call to malloc to create the node, and then there was a call to malloc to make space for the name. You have to make sure that you're freeing the memory for the name as well. And so the way we fix that is with this version of better string. So let's look at its pop function, and I'm going to put the 2 versions bad string next to better string. And you'll notice there's just this one tiny difference over here. So on line 35 in bad string.c, I'm freeing the old. But on line 35 in better string, I'm first remembering to free the name. So I free the name, and once I free the name, then I can free that old head as well. Questions on that one? That point can be a little tricky to get. Aaron, let's get you the microphone.
This is an unrelated question to what you just described. Could you scroll down a bit on bad string? It's just regarding one of the memory allocations.
Okay, bad string. Tell me where you want me to go.
Their head point daughter. I was just wondering, with the malloc, string length doesn't give the length of the null byte as well, correct?
No, it doesn't.
So, oh yeah, it's +1. Okay.
Yep.
So when it was like cut, I didn't
It was probably just cut off on the side a little bit.
Yeah. I was just wondering why there was no +1.
All good.
Of course.
Think where we were going. Okay, any more questions on that before we move on to Bingley? You've already got a microphone there.
So although there is a bug, but the program can run correctly in a short period, right?
Yes, so that Bingley brings out this really important point. So even bad string.c will actually run, and you won't be able to tell that something is going wrong unless you start using it a lot. So if we create lots and lots of string elements, and then we pop a lot of nodes, and then we add a lot of nodes, what's going to happen? That's a question for you, Bingley. What will happen if I do this over and over and over?
You have lack of memory.
Yeah, we'll have a lack of memory because we keep asking the computer for more memory, but even when we're destroying the nodes, we're not giving back that chunk that we're using for the name. And so that just gets left in the computer's memory, and it has marked that out as belonging to our program, as already being allocated. So we get what we talked about a couple weeks ago, we get a memory leak. Just like we talked about how when Google Chrome has a memory leak, it can slow down your computer. Even when you close all the tabs, for some reason, Chrome is still using vast amounts of memory. This example is an example of why a programmer might make that mistake. Because up till this point, you said, okay, I'm mallocing all the nodes, I'm freeing all the nodes, I don't have any problem. But if you forget this kind of extra step, you can end up with a memory leak anyway. Aaron.
Could an attacker like exploit that if the memory hasn't been freed and it's still somewhere there? Could they like find a way to search through the memory and then find something that hasn't been freed?
A memory leak on its own for an attacker is mostly going to be useful for slowing down the computer if you can trigger more and more memory, a larger and larger memory allocation. In terms of using that memory allocation as part of an exploit, that would require another bug as well. But it can be useful. It can also be useful if you're trying to later leak things in memory because that memory has not been reused, it's still been allocated, and so perhaps there's some data in there that someone else can exfiltrate later. But again, it's going to require a little more subtlety than just a memory leak to do something with it. More questions? Tim, do we have a microphone? Yeah, Bingley's got it.
For those of us who have done Python in FOC or elsewhere, are the lists, we don't have arrays in Python, right? We've been familiar with lists. So are the lists in Python implemented as linked lists or are they something else?
We can, in the next break, we can actually look at the code that Python uses to write Python and determine that. Python lists are probably like, I would be relatively confident, but I'm not certain. We actually would have to check. But the sensible way to implement it is as an array with dynamic resizing under certain conditions. But the interesting thing about Python lists is they can have different items in them, so different types of Python objects. So what you might get is an array of pointers. And each of those pointers points to a pi object. I think that actually is something like what it's doing is there's a pointer to a pi object, and then that object itself can store different types of data. So just like in a C array that you can have, in theory, strictly speaking, you can't have different types of data in a C array. But your array type can be an array of pointers, and each of those pointers can point to a structure that identifies what type of memory it is connected to and also has another pointer to that object itself. So to maybe make that a little more concrete, this is all bonus information. You could have a C array that is full of, let's do struct pi object, and this could have a char star type, and it could have a void star data. And then you can have an array of different pi objects. And then an individual pi object might look like something like this. Forgive the fact that I'm doing this outside a function, but then you could have something like that. So then the pi object has a pointer to an integer, and it has a string indicating that it is an integer. So that could be, oh, I need a name for this pi object. Pi object 1. And then I could have another pi object 2. Something like that. And so now our array actually has like two different kinds of things in it, even though they're both really struct pi objects. And so if you were trying to write the code to make a Python style list, but to write that code in C, which is actually what Python does, this is one way that you might go about actually making that happen.
That makes a lot of sense. You mentioned that in Python, the arrays are dynamically resizable, unlike in C. Could you have a way of going about that as like a linked list of arrays? Like say you ran out, in the example earlier with the queue, we ran out of space in the queue. That we decided to go all the way and run a linked list. But another way to preserve a lot of the benefits of an array and get the extra benefit of being able to resize would be just like, oh, okay, we've run out of room in our array. Let's make a new array and just make like the last element of the old array the link to the new array. And that way we can like not have to deal with the like time complexity costs of dealing with linked lists.
So then you end up, that is a very legitimate way to do things, and operating systems use something like that to manage memory internally. The problem there is then you're allocating different chunks of different sizes around the place. You can run into memory inefficiencies if you need to do something that requires you to copy a whole chunk at once, because you might be able to copy like a chunk of 16 elements very quickly using a modern CPU, but if copying a chunk of 8 here, a chunk of 2 there, a chunk of 3 there, gets very expensive. There are other things like the computer has, aside from its RAM, it's got temporary, even faster storage than RAM, but that is going to rely on things being in contiguous chunks. And then the last kind of issue with doing things that way is you can end up with memory fragmentation, where your entire system memory is in chunks of 2s and 3s and 4s and 5s and 6s, which compounds all those efficiency differences. But again, that discussion is somewhat outside the scope of FOA. We ready to move on? Okay, all good. So now I'm going to give you some code that you can use in your future assignments. You will not in this class be required to write your own linked list code from scratch. When I had to do it in my 3rd year of uni, I messed up so badly it nearly sunk my entire group's semester-long project because I had bugs in my linked list code. I've now learned ways to make sure that my linked list code is correct, using things like invariants and proper tools. But because you're all still taking a first-year subject, we are providing this pre-made code for you. So this is listops.c, and feel free to go through this and look at the code yourself, but it's just a very clean implementation of what we're doing that was written by Professor Moffat. So it's almost exactly the same as we've been done, just all pre-written nicely for you. And then we have listeg.c, and these will be available linked from the slides. They're also in the textbook. They're also on Alistair's website. And here is an example of a slightly cleaner way to actually run all of this code. So we were writing it from scratch, and if you were designing it nicely, it'll have some of these features that Alistair's version does. So now we can compile listeg.c and then run, oops, this is probably going to be called a.out now. Run a.out. Call it listeg, just to make sure, listeg. Oh, it's waiting for a scanf. Whoops, it's wants a list of numbers from me. There we go. And now it has made a linked list containing the elements that I have added. Let's just do that with numbers that are slightly different to make it easier. So let's do it with 1, 2, 1, 3. So it added the number that I asked for, and then the number plus 1, and then the number plus 2. But notice here that the ordering is important because here I inserted at head, the first item, and then on either side of it, I inserted one of those items at the head, and the other item I inserted at the foot. So tail and foot are kind of synonymous. You can use either terminology. You can use, there are a bunch of different words that people do use. Have a play around with that. Write your own little basic linked list code. Not the code from scratch. It's worth doing some of the stuff from scratch as well, but for the class, you at least need to be able to play with this existing library. Okay, let me look at one other function here.
With how it is list equals, insert at head, list, and I.
And see if we want to go through this one. I think we are probably fine not going through that one. Okay, that was a whole lot of work on linked lists, but now we're running into some trouble because memory is getting complicated. As I think Bingley pointed out, we can run into memory leaks. Lara helped us step through where we had a pretty substantial bug. And this is going to create problems for us as programmers because if this is the kind of mistake that even I as a slightly more advanced programmer make, chances are when you write programs, this is going to be a nightmare. And I remember when I was a student, this was a complete nightmare for me. But it doesn't actually have to be. And this is the good news. So there are a few ways that we can kind of address the challenges with memory management getting more complicated. And I know some of you in the room will have strong opinions on this. So the first one is to use a very smart compiler. So as we've seen multiple times, modern compilers are actually pretty good at catching a wide variety of bugs. And in fact, the compiler also has additional options which make compiling much, much slower, and also which can make the program running slower, but can actually give you extra information about the types of bugs that might be present in your code. In modern compilers, one word that they are known by is sanitizers. And this is just a fancy term for like a bit of extra code that your compiler is going to run and inject to try and detect these extra bugs. So let's try and run our badstring.c, I think. We won't do that with a compiler tool for the minute because I've forgotten the compiler arguments for it. I will fill that in for you later, what compiler arguments you can use. But there are also other tools that can catch errors as your program is running and report back on them. Now, the best of these tools is one called Valgrind, V-A-L-G-R-I-N-D. The problem for many of us, though, is that until, I think it was March 13th, Valgrind did not support the new Macs, the M series of Macs. The great news for us is that in a couple of months, Valgrind will support the new Macs, but until then, we can use the tool within ed and within vscode.dev to actually run it. And what Valgrind is going to do is, it's got a couple of tools built in, but the tool that we're going to be interested in for now is it can monitor every malloc you do and every free you do and match them up and tell you, okay, here is a malloc that you made that never had a matching free. So please go back and check your code and look for where you should have freed this piece of data. So let's give an example of running it on badstring.c. So I have some instructions over here. So let's just compile badstring first. Badstring.c. Okay, and now I'm going to run the tool Valgrind with the argument -- leak check equals full, and I'm going to run it on badstring. Okay, and then a few seconds later, it will have run the program and give me this fairly large summary about how I used the heap. And let's go through a couple of different pieces of this. So it tells me when the program ended, there was still 23 bytes in 4 different blocks, in 4 different chunks that I'd allocated but had not freed. So the way that the operating system behaves is when the program ends, it is going to free the whole heap, but this is still an indication that by the end of the program, I still hadn't remembered to clean this stuff up. And this just gives me some stats about overall how this is in proportion to my program's overall use of the heap. And then what it's going to do is it's going to provide a report on each of the times that some of the data was lost. So now I'm going to go back to my compiler and I'm going to add an additional flag here, the -G flag. What the G flag is going to do is it's going to add extra information into the compiled version of the program that tells that if you were to open up the compiled program, there would actually be indications of the line numbers in my original code that correspond to each of the machine code instructions that have been put into my compiled version. And why is this useful? Well, it means when I'm trying to debug my code later, that I can go back and can say, oh, at this line of machine code, there was a stuffed up memory allocation, and this is equivalent to this actual line of my written code in C. So now let's run Valgrind again. I'm going to clear, run Valgrind again. And now you can see this has changed a little. Now it actually has badstring.c, line 50, okay, and then at line 50 in badstring.c, it did insert at index, and this was at badstring.c line 87, and then insert at index called malloc. So let's look at line 87 in badstring.c. So line 87 is where I've malloced the space for that string, for the name. And remember in badstring.c, it was the name that we had forgotten to clean up properly. And so what Valgrind is telling us is that at line 87, you mallocked something, and that was the thing that you never freed. So I can see very clearly that, oh, I must have somewhere forgotten to free this name that I had mallocked earlier. And I didn't just do this once. I did it a second time here, another time here, and then this one is, I'm not sure what that one is. That one might be spurious. Line 46. Oh, no, it's not spurious. This is telling me Valgrind was right. It's also telling me that I forgot to free the name for the original head node that I'd created as well, and that's why it's at a different place. So by running Valgrind, you can often spot these errors, and sometimes these errors might just be a forgotten free, and other times it might actually be a mistake in the way that you've been manipulating the linked list as well. So that can be quite a powerful tool. Now, if you are on a Mac, I've included here another program that you can run that doesn't give as nice output as Valgrind, but that will still work. It's called Leaks, and that will give you similar-ish information. Happy to discuss that more on Ed if anyone is interested. But soon there will be, very, very, very soon, there will be a way to run Valgrind as normal on the modern Macs. So you will be the last year of FOA that has to deal with the headache. Oh, here we go. That is full of bugs. And you can download this program. I'll put it up on my website, and you can go through and see all the different tools that you can use to try and detect all these bugs. So first up, I have mallocked some memory that I have not freed. In this example, I am mallocking something, using it, freeing it, but then trying to print it after I've already freed it. In this example, I have an array that has only 5 elements, but then I have a greater than or equals sign in the loop, and so this will be a loop out of bounds. In this example, I am incrementing an integer past the maximum allowable value of integers. So I have a whole series of bugs in bad.c. We can see what happens when we run it. It does give me one warning. And it kind of runs. Does some weird stuff, but it does run. But we know that this code is bad, and in fact, in certain instances, code like this could actually be exploitable. So someone could use this as a way to take control of part of your computer. So now let's run another tool and see how much more information it can give us. So I'm going to run my compiler. with some extra options. And I've turned on one of these sanitizers. And you can actually Google this. You can look up all the different sanitizers that are included in your compiler. Here I've turned on the address sanitizer and I've turned on all the normal warnings. There are warnings that aren't turned on by -wall, and you can also look those up. So let's see what happens now. Now it's run bad. Oh, when I now run bad, it does this whole big thing. So let's take a look. Error heap use after free. And so it's actually able to point out, it's not doing a good job of actually doing the reference to the line in my source code. There's probably a flag that I've forgotten, but it has at least identified the fact that I've got a use after free here. So that was one of my bugs. And then I can run, if I turn the heap use after free off, let's turn this one off. So recompile it. So it's still giving me an error. What's it found this time? So now it's found a buffer overflow, which is what was happening in when I used out of bounds access. So another way to describe out of bounds writing is a buffer overflow, because I have a buffer of only so many bytes available to me, and I've overflowed the buffer that has been given to me. And that's also kind of where the name Stack Overflow comes from. For those of you who use the site, it's a similar idea. You have a certain amount of memory and you've used more memory than is actually allocated to you. So one thing you'll notice about the sanitizer here is it's like Valgrind, it's dynamic. But what's happening is as soon as it encounters one of these bugs, it actually crashes the program. So you might have multiple bugs and you might have to fix them one at a time so that you can actually get the full advantage of the tool. So now if I turn off my out of bounds access example, let's turn that off. And now it has detected memory leaks. So this program is never going to be bug-free, but you can see that by running the compiler with the special sanitizer flags, I can actually go through and detect all of these different types of bugs. And that is a very powerful tool. So this seems like a great way of writing secure code. What would be another way of writing more secure code that is a little more outside the box from what we're doing in class? What is the root of all of these problems? Sia, are you the root of all the problems? The program is. There's something else, though, that is making our life very difficult. That you've all programmed before this semester, right? Or many of you. Right. What is different about this semester that is making life hard? Tim?
Memory?
Memory, yes.
To deal with allocating and freeing.
And why do we have to deal with it?
Because we're in C.
Because we're in C. Sorry for cutting you off, Tim. So really, one of the best ways of actually fixing this problem is to use a language that has been designed to help you avoid these types of things. And so there is a field of computer science known as programming languages, which is about the theory of designing programming languages that are effective for the purpose of which they were designed. Now, C originally was meant to mimic the low-down details of the way machine worked and to expose that all to the programmers. But the byproduct of doing that is it has lots of these potential traps and what we call foot guns, because you can shoot yourself in the foot with C very easily. And so one thing that I encourage a lot of my students to look into is other types of programming languages out there that have been designed with different purposes in mind. So for example, there is a language called Rust, which is kind of similar to C in that it's designed to go to very, very efficient machine code. But it's very different from C in that it enforces a lot of things to stop you from shooting yourself in the foot and having all of these memory types of issues. Python as well. Python is very much slower than C, multiple orders of magnitude, but does help you avoid these memory management issues. So Python is going to be good where you have a task that doesn't need to be super, super, super high performance, but where memory safety and the ease of writing code can be valuable. And this is one of the things that is useful to take away from this class, even though it's not our focus, is that different programming tools give you different advantages and disadvantages. And this is definitely one of the big disadvantages in C. However, C is still very, very widely used in a large number of places. It serves as a great foundation for learning a variety of other types of languages, including things like C++, which get used in video game development very, very heavily, and also for large enterprises often use C++ if they have a more sophisticated development shop. Any questions on memory safety, tooling? Tim, you got a microphone?
So with C, the memory thing is definitely an issue. I feel like another thing which I found difficult with C is the fact that its syntax is so different from Python. But this feels to me like it's not really essential to the core of what C is about. Like the fact that, you know, you use curly braces instead of indentation, this seems quite arbitrary, not essential to like the key character of what differentiates, say, C from Python. So I wanted to ask, has there been any effort to create something that is more like C or C++, but uses a more modern syntax, given that the syntax seems quite separate from the underlying properties of the language itself, like the fact that it's like rigid types or whatever?
So I'm not a programming languages person, and there are lots of attempts out there to fill all parts of the different design space. In my mind, the language that I can think of that's probably closest would be something called Julia, which is designed for relatively high performance in scientific computing, but with more Python-like syntax. And so that's something you could look at. But there are lots of different niches in the programming language world, and so it's worth, like, just for fun, taking a browse on Wikipedia list of programming languages and taking a peek at them. It's something you might enjoy. Any other questions? Yes, yeah. There we go.
So the most annoying thing about C for me was that I couldn't actually test any of my helper functions. So in the end, you just have to sort of roll with it and get a good idea of what your program's going to do. And the first time you compile it, you're going to get like 100 errors. So
yeah, so there are a couple of things that you can do to try and avoid this problem. One is just good development practice in C is to write smaller chunks of code, smaller functions, and then test each function. Another thing you can do is something called test-driven development, which is to actually write tests ahead of time and then slowly develop your program such that every time you run it, all the prior tests have to pass. And the goal of you now is to fix the next test that shows that you've achieved the next set of functionality that you want. And so that you have a guarantee that each time you compile it and run the tests, that you are actually making progress. But that is a challenge for something like C. So one way that people often like to do some development in Python is they'll open the interactive Python window, put some code in there, see what it does, and then put that into their actual program file, or use something called a Jupyter notebook or a notebook, which allows you to write small chunks and then run that chunk as if it was a cell in a spreadsheet. There are tools like that for C. They're a little harder to get running, but they do exist, so you can smooth out some of those pain points. Anything else? And I've gotten your name a few times today and I've already forgotten it. Daniel, okay, do you want to run that up to Daniel?
On the note of you not seeing like errors as you're programming, like if you're using a good IDE, it does also show you the errors. Like if you have like good LSP implementation, like, I don't know, ClangD.
Yeah, so I'll give a brief remark on that. One thing that I'm doing right now, one of the reasons I like using vscode.dev is by default, or cs50.dev, by default, it's not showing those error messages, which I'm intentionally hiding for educational purposes so that it doesn't just give away where the bugs and faults are. However, if you are using a modern text editor, it is a useful and important feature to have that it will do a form of static analysis where as you're coding, it runs tools over your code to try and spot errors for you, and then we'll like put a red squiggly line under something that it thinks might be wrong. And that is an incredibly essential part of modern development as well. Anything else? Okay, we are ready for a brief summary slide then on some of the stuff we've covered today in terms of data structures, which is just to go over the difference between arrays and pointers in terms of the big O worst case complexity of some of the operations involved in their use. And this allows us to choose which of these might be more appropriate for a given use case. So for example, arrays are really, really fast to access the kth element. So if we're going to be doing arbitrary accesses to somewhere in the middle of our data, then it makes much, much more sense. If we're going to be doing that a lot, to use an array. Because for a linked list, if we're looking for the kth item, that's going to take us O of k steps, which is worst case O of n, because k is bounded by n in this case. And that is not something we want to be doing over and over and over if we can just be doing it at O of 1. A push in an array, to put something at the very first location in the array, is going to require us to copy the second item to the third place, the third item to the fourth place, fourth to the fifth, like Aaron had earlier. And that's an O of n operation because we're going to have to do n copies. Not very efficient. But for the linked list, it's as simple as taking the first element and then just joining up its pointer and updating what you consider to be the head of the list. So O of 1, very fast. Likewise with pop, it's the same thing for an array. And for an array, if you want to remove the first item, at least the naive way of doing it is then having to copy everyone up one place forward, which again, O of n, not very efficient, but we can do it O of 1 with our linked list. We just remove the item and the new thing that's left, we remove it, we free it, and then the item that's left that was previously the second item is now the first item. Very quick. Inserted end is efficient for both of them, under the assumption that we are keeping track of where the tail or the foot of the list is, which doesn't take very much memory, so that's probably a recommended practice for linked lists. And then to insert at the kth position, this is where it's going to be somewhat expensive for both of them. Ronald.
The pop is removing the end.
Can we get him a microphone? Daniel has it.
Hello?
There we go.
About the pop, is the pop removing an entry at the beginning or the end?
It's at the beginning.
Because I remember in Python it's removing at the end, so this is just a different definition?
Yeah, it's just a different definition. Yeah, I don't have much more to say there than different definition. I think I got confused earlier on in the lecture as well, and I might have said the wrong thing. So one thing that we'll be doing here, when I talked about the array, when I was talking about our data structure over here, I was using a bunch of different terms to refer to what was going on. Not only was I referring to it as, say, an array or a linked list, but in the Taylor Swift example, I was really talking about it as a queue because that's what it is. We would only ever, for most of the example, we were only ever removing things from the front and adding things to the very back. So we were inserting at the tail and removing from the head, which was our pop removing from the head and then our inserting at tail. And this is really the behavior that we expect of a queue generally. It doesn't matter whether it's implemented using a linked list or whether it's implemented using an array. That notion that there are only really two operations that we care about is similar whatever implementation we use. So in this instance, we can think of lists, stacks, and queues as abstract data types, where we can implement them using an array, we can implement them using as a queue. What really matters is the operations that we have optimized it for and which ones we permit ourselves to do. So for a queue, we should never be allowed to insert something in the middle. Not a real life queue, a computer science queue. For a computer science queue, the rule is the only things that you can do is remove something from the front or put something new at the back. A stack is somewhat different. A stack is remove from the front, add to the front. And then a list has the behavior where you can insert at the front, remove from the front, insert at the back, remove from the back, insert in an arbitrary position as well. And these things, while when we talk about them are different, when you actually go down to the level of the memory inside the computer, the memory is still the memory. The only difference is how you're deciding to use it. So if we set it up in the way that we're using pointers to refer to chunks that are located in different places, then we can get the behaviors that we saw in our table associated with the pointer version of the linked list. If we are only using contiguous chunks of memory at a time, then we get the array behavior. And we can use either of these methods to create any of these three abstract data types. It just might be more or less efficient if we choose to implement one of them using the wrong underlying data type. But the useful idea of these three abstract data types is here we are we're abstracting away the order of access from the order of arrival. This means that we are separating these two things conceptually. So all of these have different behavior with respect to when something was added and when it gets removed. So with a stack, that is last in, first out. So think of a stack of plates. The last plate that you put on top is the first one that you can remove, and a queue is somewhat opposite. So a queue is first in, first out. And so in this way, these allow us to, whatever order the things came in, we can have rules about what order they come out and implement that using our data types. Now, the other thing we've done here is we've abstracted away the data type, or our abstract data type, away from the algorithm that we're actually using to implement it. So implement it using arrays or implementing it using linked lists. The core thing here is that we can have our data type, the way we view the world, that is then implemented in multiple different ways. And we can also abstract away further the specific low-level data type from the algorithm that we're using. More specifically, let's say we're doing a sorting algorithm. We can do a sorting algorithm on an array. We can do a sorting algorithm on linked lists. We can do a sorting array on a linked list of strings. We can do a sorting algorithm on a linked list of integers, a sorting algorithm on an array of integers, a sorting algorithm on an array of strings, and still have written the same algorithm. And when we do this in code, where we've written the algorithm once, but it allows us to run that algorithm over multiple different types of data, we call that polymorphism. And polymorphism is just means many forms. So a nice example is of polymorphism in the real world is a vending machine. You can put lots of different types of items in the vending machine. So let's say we have type is water bottle, type is chocolate, type is drink, type is chocolate, type is snack. But the interface that the vending machine presents to the world is the same no matter what kind of thing you want to buy from it. If there were a pair of earpods in there, or what are they called, the Apple ones? AirPods, that's it. If you have a pair of AirPods in there, the interface to the machine doesn't change. The interface is type in the number, tap your card, and then out of the slot comes item. What the details of the item happen to be don't matter. The type of the item don't matter to the interface of the machine. And this is what polymorphism in our code is as well. We can imagine that our algorithm is equivalent to the machine, and it's going to present the same set of arguments and output mechanisms no matter what kind of data type we're running it on. So as I just mentioned, we can think about this even with data types that are a little more complicated than our simple ones of int and char. So we can sort numbers, we can sort words, and we talked about lexicographic sorting, which we had to define what sorting kind of meant for that, and we could sort presidents from best to worst. And I'll leave that to you. I certainly haven't included the current president on there, and you can decide on your personal ranking. Fortunately, we're in Australia. I'm not putting up the candidates for this coming weekend. But this kind of leaves us with an interesting question of what does it mean to sort presidents? So we could sort them in order of age in which they appear there. We could sort them in order of best to worst. We could sort them in order of appearance. So the 45th for the 44th president as opposed to the 43rd or the 42nd. The same way we could sort words in a bunch of different ways. We could sort words lexicographically, or we could sort them from our favorite letter to our least favorite letter lexicographically. And numbers, I think, are at least a little more defined in terms of sorting. But what does it actually mean to sort implicates a somewhat deeper question of what does it mean to actually order things. You can't have sorting without some notion of order. So, like any good professor, I asked Wikipedia. And this is Wikipedia's view of what it means to order. Now, we could use this more formal definition, and this is correct. I checked it. I wasn't just trusting Wikipedia. But for our purposes, this is really going to be sufficient for us. What we want to do for any pair of items, we want to ensure that that there is a definite answer to each of these questions. Is A equal to B, or in our ordering, is A greater than B, or is A less than B? And we use this to define an ordering. Vincent.
But what happens if you have, say, complex numbers?
If you have complex numbers, then you have to add some complex numbers, as far as I know, do not have a total ordering. Yes, the people who actually know maths in the audience are telling me I'm correct. You could define an ordering on them, but they generally do not have an ordering. At least not a natural one. So now what we're going to do is we are going to look at an example of polymorphism in actual C code. So qsort is kind of deceptive here. You might think it stands for quicksort. It is not actually quicksort, despite the fact that many people in the world think it is. It is just a fast sorting algorithm. So let's take a look at call qsort. And this is a library function. Qsort is going to take in a number of arguments. It's going to take in something that we're going to want to sort. Then it's going to need the number of elements, the size of one of those elements, and then most importantly, it's going to need some function that actually tells the sorting function how to compare different elements such that there is actually going to be a well-defined ordering of all of the elements. So in this case, I have a function, I have the name of a function here called string ascending. And what this is going to do is this is going to be a function that will take in two elements and return an answer to the question we had before. Not that one, this one. Right, so we need to define a function which, when given a pair of items A and B of the same type, is going to yield an answer which of these cases is true. So let's take a look at the way we actually implemented it here. We kind of cheated. So we said that a function which tells you if these two elements are in ascending order or not is just the string comparison function. And we know that that returns 0 if they're equal, -1 if B is bigger than A, and 1 if B is bigger, or at least positive and negative values. The only thing happening here that's kind of special is that we are doing some casts to make sure that we are in the right types, and I'm not going to worry too much about that right now. The other thing here is we are using a new keyword in C, the const keyword. And const is the way we can declare a function to let the compiler know and let other functions know that this particular function, the string ascending function, is not going to modify either of its arguments. It will look at them. So string comparison looks at both v1 and v2, but it's not going to modify them. You might ask, why do we do this? This is to enable more effective static analysis, largely, so that when the compiler runs, it can tell us, oh, you said you weren't going to modify that, but you have, and then you know, oh, I had a bug. The string comparison function isn't actually meant to change my strings. Aaron.
I was going to say, is that why we can't use macros and define a one-line function?
You'd probably get some errors. I think there is a way of doing it with a macro. It's ugly and will result in trouble. Part of the reason is because when we put the name of the function there, we're actually using some slightly deeper. Have anyone seen the iceberg meme of like the things at the surface and then like the very deep knowledge underneath it? So this is like maybe it's still above the waterline, but well below the peak. Every function in C, if you just use the name, is a pointer to that function. And actually what qsort takes as its argument over here is a pointer to a function that it's then later going to use. Why? Well, what it's going to do, deep inside qsort, there'll be some line that says, figure out what function the user gave you, dereference that function, and dereference it with the arguments for A and B, the two items that we want to compare. Do we have a microphone for Sam?
What type is a function stored as in memory?
It's stored as the function itself, or the contents of the function, or the function pointer?
Well, the function pointer I assume would just be a pointer, but like how can you have a pointer to a function? Like what's actually in the pointer?
So it's not a standard C type at that location, it's just an address. But what you can do is you can tell the computer, run the commands located at this address. And that's essentially what's going on.
Right.
So there's no like specific type. I mean, we could invent a type and the type would be instruction. And the instruction type would be dependent on the particular design of your machine. So if your machine, for example, has instructions that take up 4 bytes for each instruction, which in some instances is common. So then you could say this is every 4 bytes is a new instruction, and what we have really is an array of those instructions, and you could modify them if you wanted before actually running the function. Although there are some caveats around that to stop people from exploiting that fact and overriding your own code.
Right, okay.
Let me see if I can bring up the man page anyway. Okay, I'm trying to make this big enough. Okay, there we go. So we can see our function prototype in the man pages for qsort. We have there we go. We have the place at which it should start looking for elements. So it's going to take in an array or a pointer to a chunk of memory, really. It needs to know every time it wants to look at a subsequent element, how large the jump has to be. So that's the width parameter here, is like how many bytes down do I have to go before I get to the next element to compare. It needs to know the number of elements in the array. And then it has this complicated looking thing, which is the signature, the type signature for a function pointer that is able to accept 2 arguments to compare and returns an integer. So you can see here it is returning an integer. It is called compare, and the way we know it's a function pointer is because of this stranger syntax by wrapping it in parentheses and then having the parentheses after. And then it takes in 2 arguments, a constant void star and a constant void star. And this is where, even for me, sometimes reading type signatures can get a little tricky. There are a bunch of fun tools online where you can type in a really complicated looking C declaration and it will actually tell you in plain English what that type signature actually is. So I'll see if I can very quickly pull one of those up for us. And ChatGPT can probably do it reasonably well as well. So this site is called cdecal. C gibberish to English. And let's try one of these examples. So what is this? Foo is a pointer to a function void, returning pointer to an array of size 3 int. Still a little more complicated than probably is helpful for us. But let's take this function pointer over here and put it into cdecal. Declare compare as a pointer to a function. And then what is that function type? The function has 2 arguments, a pointer to a constant void and a pointer to a constant void. So this is just void star pointers. And the reason we use void star pointers is to allow people to substitute in a pointer to whatever type of object they like. So it might be a void star pointer that's really pointing to an int. Or it might be a void star pointer that's really pointing to a string. And then this whole thing should return an integer. And you can use this as another tool to help you get your head around it. So all we want this to actually do for us is to sort koala, kangaroo, quoll, quokka, wombat, goanna, wallaby, bilby in ascending order using string compare. So GCC, call qsort, And now we see it's sorted. That is great. So we had a question earlier from, I think, Tim. Let me blank that again. So we had a question earlier from Tim saying, well, why do we only have like a pointer to what's in front of you and behind you inside our linked list? What if I added like other pointers to other things all around the place and use that to try be efficient? Well, it probably doesn't make much sense for our line of people wanting to go see Taylor Swift. So you can imagine like a multi-dimensional. Tim, was this your question or was it someone else?
Yeah.
Yeah. So we could imagine a multi-dimensional line of people waiting to pick up their tickets. That probably doesn't make much sense. What we are going to do in our next lecture is we are going to start looking at data structures that are a little more complicated than this one-dimensional forwards and backwards, that allow us to tackle different types of problems that, unlike this queuing problem, might actually be more useful to have different ways of representing the data, and that will start to unlock ever more sophisticated algorithms and ways to process things in using a number of techniques that you might find surprisingly efficient. And with that, thank you very much. Good luck on the rest of your assignment. Extended till Monday. Assignment 2 will be out Tuesday. I will see you all next week.